Hi, students. Instead of uploading the entire lecture video from today's class, I thought I would summarize the brief takeaway points from today's class held on November the 10th, 2022. So in this small video, I'll cover all the items that we had discussed, and I'll try to keep it short, under 10 minutes. So in today's class, we discussed the concept of direct mapped caching, wherein a memory address, a given memory address maps to a very unique location inside of the cache, and therefore it is called as direct mapped. Now, the great thing about direct map is it is going to use the bits of the memory address to determine where exactly an address, a memory address, will be cached inside of the cache. Now, there are certain questions that we need to answer in order to determine the bits that need to be considered in order to perform this mapping. The very first question would be, which byte are we referring to? The next question would be, which word in a given cache block we are referring to? Then finally, the last question would be, to which block we are going to map a given address. Now, since we are dealing with MIPS 32-bit architecture, there is going to be 4 bytes in a given word, and therefore you would always require 2 bits to access a given byte in a word. The next comes the word offset, which is going to vary from architecture to architecture. Specifically, the number of bits is going to vary from architecture to architecture. Now, in this case, since we are referring to 4 words in a given block, we would need at least 2 bits to access one of the 4 words. And therefore, the word offset in this example of 8-block direct map with 4 words per block is going to be 2. So word offset is equal to 2. The number of blocks in the cache is going to determine the number of bits needed to index them. Since we are using 8 blocks in our cache, we need at least 3 bits to access one of the 8 blocks. And therefore, the number of index bits is going to be 3. The remaining bits is going to be referred as the tag bits, which are going to be used to differentiate between multiple addresses that map to the same word, or rather the same cache location. Please note that our cache is substantially smaller than the main memory, and therefore multiple memory addresses may map to the same block, and we need a mechanism to differentiate between them. And it's the tag bits that differentiate between multiple memory addresses that map to the same block. We can generalize this for our specific scenario of MIPS 32-bit architecture, where the number of address bits is equal to 32. The last 2 bits will always be for the byte offset, and it's going to be fixed because we have 4 bytes in a given word. Now, the number of words in a given block can be variable, and therefore the number of bits used to represent the word offset is also going to be variable. It will vary from cache architecture to cache architecture. So let's assume that we have 2 to the power of m words in a given block, and therefore we would require m bits to access a unique word in a given block. The number of index bits will also vary from cache architecture to cache architecture. So let's say that we have a cache with 2 to the power of n number of blocks. In that case, the number of index bits is going to be n. The remaining bits is going to be, or the remaining bits are going to be reserved for the tag bits, which are going to differentiate between memory addresses that map to the same block. So let's consider a very specific example here. So let's say that we have 8 blocks and we have 4 words per block. Therefore, the value of m, the number of bits used for word offset, is going to be 2, because 2 to the power of 2 is equal to 4 words per block. So the number of bits required to access one of the 4 words is going to be 2. Now, since we are referring to 8 blocks, the number of index bits is going to be 3, because we need at least 3 bits to access one of the 8 blocks. Consider a memory address, which is 101010000. Let's see how this maps. The index bits are given in bold right here, 101, which tells us that this address is going to map to block number 5. Further, the next set of bits, 00, those are the word offset. The word offset tells us that we should be looking at word number 0, because 00 corresponds to word 0. If this were 10, we would be looking at word 2. In this case, since word offset is 00, we are looking at word 0. The last set of bits is going to tell us which byte this address is going to refer to. So in this case, it is 00. So we are looking at the very first byte. If this were, let's say 11, we would have been looking at the third byte. And that's how addresses map to a unique location inside of this direct map cache. One additional note that I would like to make here is initially, since the cache is empty, access to the address 01010000 is going to result in a miss, and because the valid bit is set to 0. And therefore, what the hardware is going to do, it's going to fetch a cache line worth of information from the main memory, and it is going to stick it in right here, and it will change this valid bit to 1. Specifically, what's going to happen is all the addresses from 0101 0000, which is this starting point right here, until 0101 1111, which is this location right here, they all will be cached inside of this cache line. And the value of this valid bit will be set to 1, and the tag bit will be 0, because our tag bit is equal to 0 in this case. We are going to talk about getting a cache line from the main memory and putting it into the cache, and the concept of hits and misses in our class on Tuesday. For this class, the only takeaway messages are as follows: the definition of direct map cache, how the memory address bits are used to identify the particular block, the particular word in a given block, and particular byte in a given word. That's all you have to understand from today's class. More on this in our next class on Tuesday. Thank you for listening.